Hi, my name is Muhammad Arif Bizainuddin. My matrix number is 105175. We are from Group 7. We want to present group project presentation for subject computer architecture. This is our group members. So the question 1 will be presented by Ransham, Muhammad Mike and me, Muhammad Arif. And the question 2 will be presented by Emmanuel, Lambert and Andre. Introduction. This project examines how modern computer systems optimize performance through instruction execution and memory access, focusing on reduced instruction set computing (RISC) and cache memory. Objectives: to understand the fundamentals of RISC architecture, focusing on how it simplifies and optimizes design enhances CPU performance and execution efficiency. To understand how cache memory improves CPU performance by minimizing access time to frequently use data and evaluating how different cache configurations impact program execution efficiency through simulation. Question 1. The question 1 involved in three phases. 1. Design a small instruction set with at least 6 instructions: load, store, add, sub, jump, and halt. 2. Write a program using C language that stimulates CPU with the application of fetch, decode, execute cycle. 3. Run the simulation to show the output of the program. This is our program, RSC program execution diagram. This diagram shows from step 1 until step 8. This program will be turned into C program, where Ransham and Mike will explain later. Operation codes. Operation codes for our program is load for 0, store 1, add 2, subtract 3, jump 4, halt 5. Opcodes. Based on RSC program in the diagram 1 and 2, the opcodes such as 010, 011, 211, 112 is 3 bits because to represents at least 6 instructions in this project. 3 bits can represent up to 8 instructions, so it is suitable. Instruction can be calculated, such as 2 the power of number of bits. So when the number of bits is 3, so 2 the power of 3 equal to 8. The purpose of opcodes is to direct the operations of the CPU. Operands. The operands is 4 bits because the binary has 4 bits long. We get binary by dividing number repeated division by 2. For example, address 10. So we'll be dividing 10 repeated division by 2. So the binary number take from remainder from bottom to top, which is 1010. The purpose of operands is to determine the address used for data retrieval or storage. Binary forms. How the opcodes and operands are structured in binary form before the execution. Example from step 1 and step 2. Step 1 and step 2 show the program want to load the value 5 in address 10 from data memory. Opcode for load is 010. 0 is operation for load. 10 is instruction address. Address 10 in 4 bits binary is 1010. So the full 7-bit instruction, which is opcodes and operands, is 0101010.
Let's walk through a simulations of basic CPU instruction cycle using C programming. This could simulate how a CPU performs operations like loading data from memory, doing arithmetic, storing result back to the memory, and halting executions, just like a real CPU using a fetch, decode, execute cycle. We begin by including a standard input-output and standard library header, which are necessary for printing to the screen by using functions like exit. Line 5 to line 6 to 7, define memory size and register count. Line 10 to line 15, define the operations code. Define load operations to load value from memory to register. Define store operations. 1. Store value from register to memory. Define add operations to add to register. Define subtract operations, subtract to register. Jump operations, jump to another instructions. Halt operations to end the program. The next one, type type def structures, structure name, instruction structure. This structure represents a single machine instructions. Tells what the operation code tells what operations to perform. First operand target register or jump locations. Second operand memory locations or source register. Third operand optional second source. Then we go to line 27 to line 13. It's for CPU core components. Tracks integer program counter 0 to track the instructions being executed. Instruction structures, instruction register temporarily holds the current instructions integer register array in array number of register. Our general purpose register. Float main memory inside array memory size equals 0 to simulate a main memory RAM. Line 34 to line 14. This is a structures for sample program. Then line 42 is to count of instructions. Line 44 line 45 to line 15 is the step 1 of fetch instructions. They will copy instruction from the program. Line 53 to line 110. This is a step 2 and 3 for decode execution instructions. For the load operation, the load operations load from memory into a register. Store operations store from register into memory. Add operations perform additions between two registers. Subtract operations perform subtraction between two registers. And jump operations jump to another instructions to change the program flow. And hard operations to end the programs. The default to handle divide operation code. Line 114 to 121 is optional print register state. Also 124 to 129 also optional to print use memory. 132 for program entry point. And in integer main, we initialize the memory with the test values. In this part, we call all the functions to do all the step fetch, decode, executions. Step 1 fetch, step 2 and 3 decode plus execute. Then print register state shows the current register values. Print memory state show affected memory. Program counter +++ to move to another instructions.
Okay, now I'm gonna explain about the output of the code. Okay, first we can see here which is a program counter 0 and operation code is 0. Okay, first operation code 0, which is load. So it load the main memory 10 into the register 0. That's why we can see here main memory 10 5. It become the value of register 0, which is 5. That's why it become like that lah. Next we can see here which is program counter 1, which is it means that one cycle already executed and the operation code is still 0, so it's load register 1 main memory 11. So we can see here main memory 11, the value is 7. It become the value of register 1, so we can see here register 1 has turned from 0 into 7. Next, program counter 2, operation code is 2. So operation code is 2, it means that addition. So register 2 equals to register 0 plus register 1. So we can see here register 0 is 5 and register 1 is 7. So 5 plus 7, it became 12, which means it become the value for register 2, which is 12, as we can see here. Next, program counter 3 and operation code is 1. So 1 means store. So it store the
register 2 into the main memory 12. So as we can see here, our memory 12 already become 12 because we store the register 2 value into the memory 12. Okay, next, program counter 4, which is 4 cycle already executed, and operation code is 5, which is the program has been halted. So we can see the output here, how program execution has been halted. That's all.
And join Colin anak Dominic Newan. Matrix number 103332. I am from Group 7, TMF1214, Computer Architecture. Now I will present the task to cache simulation for our group. Cache simulation is a small, fast access memory used to store frequently accessed data and instruction for quicker retrieval by the Central Processing Unit or CPU. So, why is it important? First thing first, we need to know the behavior of the CPU. The CPU is extremely fast, but accessing data from the main memory is much slower. So, the CPU had to wait for random access memory or RAM every time it needed data, which would waste a lot of time doing nothing. This is what we call a memory bottleneck. To overcome this problem, the cache memory need to store access data and instruction closer to the CPU. So the CPU can get the data it needs without waiting too long. As you can see here, the memory is important because of faster data access, improved efficiency, reduced latency, and better at multitasking. Next, we move to type of cache. Level 1. It divided to separate instruction cache and data cache. Extremely fast but limited in size, typically ranging from few kilobytes to a few megabytes per core. Next, level 2. Serve as a secondary cache, larger but larger than level 1 but slower in access speed. It's shared among CPU core within a single CPU core complex or chip. Level 3, the last level of cache in the hierarchy, share among multiple CPU core or across multiple CPU sockets, larger than level 2 cache but slower in access speed. Our group decided to use two-way set associative mapping technique. It divided into two parts. One, tag bits. The tag bits identify which memory block is present. Number two, byte offset. The bit in the byte offset field decide in which byte of the block the required content is present. So as you can see here, this is the diagram of the two-way set associative. Next, I will let Emmanuel to explain the next slide. Thank you.
Hello, my name is Manuel Tawanasao, metric number 104006. So for the simulation setup, we are using Embarcadero Dev C++ version 6.3 to simulate the effect of cache memory on programming performance. And the mapping technique that we are using is set associative, especially specifically two-way set associative. So here we can see the different configuration of cache size and block size from this table, and we will be running 5 tests based on these different configurations. So this is the screenshot of the simulation in Barcadero app. Okay. This is our the result from 5 tests with different configuration applied. This is test 1, you can see here, test 2, then test 3, then test 4, and test 5. As you can see, the cache size is bigger than block size. Why? Because the number of sets. So if we divided 64 divided by 16, it equal to 4. There will be 4 sets. For this is 4 sets, 2 sets, 2 sets, 2 sets. I'm sorry. And this is Uh, and the fifth one has uh, 8 sets. So this will be the a graph, which is the two graph, which is the miss and hit and miss chart and hit and miss rate chart.
Okay, so good morning. So I'm going to explain about the effects of block size after we change the parameter. So from test 1 and 2, so if we change the block size from 16 and for test 2 is 32, the test 2 will outperform test 1, although within the same cache size, because a larger block size will reduce the amount of misses. So from test 1 and 5, although the test 5 has the cache size of double from test 1, but if we retain the same block size, it will still remain the same performance due to the performance doesn't have high workload. So moving on to the effects of cache size. So from test 3 and 4, if we change the cache size from 32 and 256. So test 3 will have the lowest hit rate and the highest miss rate, while test 4 will have the highest hit rate and the lowest miss rate. This is because that cache, the higher the cache, will generally lead to higher hit rate. And finally, so from all of the simulation that we run, test 4 is the best performing setup with 256 bytes of cache and 128 of block byte of block. Meanwhile, test 3 has the worst performing setup due to its having 32 byte of cache and 16 byte of block. This is because that limited space will lead to high replacement and misses. So we also have implementation of LRU, which is least recently used replacement policy. It's designed to eliminate the item that may access to the least recently, so that the same item will not be accessed twice in the near future. So in simple policies like as FIFO and random access, RRQ provides better hit rates for programs with temporal activity, which was reflected in our simulation result just now. So in conclusion, that we can conclude that cache memory plays a vital role in optimizing memory access performance. So if we tune parameters such as cache size, block size, and mapping strategy, the hit rate and miss rate can be significantly improved, leading to a faster program execution. And finally, that a moderately larger cache with a reasonable block size and two-way set associative mapping will yield the best balance of performance and efficiency. So these findings aligns with real-world GPU cache design, where cache hierarchy and mapping techniques are optimized for common memory access pattern. That's all from me. Thank you.